All right, so what we're starting today is looking at gases. And so eventually we'll be able to, in the same way that we looked at solutions and then kind of morph that into working with reactions and solutions, we're going to kind of do that same thing with gases here. So the first thing it has here is kinetic molecular theory. That is the theory that um, kind of explains the behavior of gases, or it outlines the assumptions that we make for the different gas laws that we're going to look at. And so we'll come back to this eventually, but the key one that we're going to focus on today is pressure. And so when you think about pressure, what you want to think about is the motion of the gas particles, and that they are kind of the frequency with which they hit the container walls. So the frequency of those collisions is what pressure is. So the higher the pressure, the more frequent the collisions are. And so we're looking here, we've got several units of pressure. And in here, we're going to be talking about standard temperature and standard pressure. And so when we talk about standard pressure, that is 1 atmosphere. So an atmosphere, or an ATM, that's a unit of pressure. There's another unit of pressure that is pascals or kilopascals. And so then another one we'll work with is millimeters of mercury, or torr. So all of those are just different units of pressure, and this kind of relates them one to the other. So if you have to convert between units of pressure, this would be the relationship that you would use to convert from one unit to the other. Then the other thing we have is standard temperature. Standard temperature is 0 degrees Celsius, or 273 Kelvin. And one of the things that we're going to look at is that with gas laws, we always work in Kelvin. That's always the temperature unit that we used on there. Okay, so let's go down. We'll take a look at this. All right, so this is a barometer. Well, an example of like what the first barometer looked like. And this was developed by a guy, and I'm sure I'm not spelling his name right, Torricelli, I think. I'm not sure that's spelled right. No, it's got 2 R's in it. Okay. So anyway, what he did is basically set up, this is a dish that has mercury in it, and then in this tube, they pulled all the air out of it, put it down in the mercury, and then so that the pressure from the air pushing down on the surface of the mercury forces the mercury up into the tube. And so when they measure millimeters of mercury, so like that unit right there, it is literally the height of that column, millimeters of mercury, which in the United States, right, when we talk about atmospheric pressure, they use inches of mercury. And so that's kind of where it came from on there. And so that's why we have this unit of pressure right there, right? So if you make a discovery in science, sometimes they name a unit after you. All right, so this is used to measure atmospheric pressure. Then the other type of a device we'll see is, it's called a manometer. And this one is used to measure the pressure of gas that is contained. And so the way it works is that when it doesn't show it, but there's usually like a valve there isolating the gas from the tube that has the mercury in it. And so when it starts out, the mercury level will be even. And so what they look at is that the way that the mercury shifts. So here, for this is an example of where the pressure of the gas is less than the pressure of the atmosphere, because when we open up the valve, it shifts it in that direction, right? The higher atmospheric pressure forces it up into the tube towards the gas, whereas over here, the pressure of the gas is greater than the pressure of the atmosphere, and so it shifts it. When we open the valve, it shifts it the other direction. And so again, we measure the pressure based on the height difference between, let me get a different color there. So based on the height difference between the two sides of the manometer there. And so here, it's kind of hard to read that down there. Here, the pressure of the gas is going to equal atmospheric pressure minus the height difference, whereas over here, the pressure of the gas is going to equal atmospheric pressure plus the height difference. Okay. All right, so we'll do a little pressure conversion here. So here it says I have a pressure of 3 atmospheres, and it wants to know what is that equal to in millimeters of mercury. Well, if we go back up to our, right, we're using our conversion factors there. We see that 1 atmosphere is equal to 760 millimeters of mercury. So we'll go down, let's see. All right, so 1 ATM is 760 millimeters of mercury. And, okay, so 3 times 760. So I get 2,280 millimeters of mercury. And millimeters of mercury and torr are identical units. So that's also 2,280 torr. And then our kilopascals, we have 3 atmospheres, and 1 atmosphere is 101.325. I think that's right. Double check. 101.325 kilopascals. So 3 times 101.325. So 303.97 kilopascals. Okay, and just kind of as an aside here, all right, one question might be, okay, why is it that we use mercury in the barometers and the manometers? And a basic reason, well, 3 reasons. Okay, mercury, it doesn't change, like its volume does not change a lot with a change in temperature. So that's one reason. The other reason is that it stays liquid at normal room temperature. And then the third is its density. Its density is, so the density of mercury is about 13.6 grams per milliliter, right? Compared to water, where the density of water, right, is 1 gram per milliliter. And so if we were to make a barometer with water instead of mercury, it would have to be like 30 feet tall to be able to measure normal atmospheric pressures. So that's kind of why we choose mercury. All right. Okay, so we're going to look at, see if my animations still work. All right, so these are the key characteristics of a gas that we'll be working with and measuring and looking at the relationships between them. And so we'll see if these are still going to work. Keep losing my mouse on this. Oh, it's not going to let me do that. Let me see. Maybe I have to. Okay. I guess in OneNote it won't let me do that. Let me see if I pull it up. Let me find the link in the notes. All right. Oops. Went too far. Okay. Oh, okay. That link doesn't work. That's always the challenge from year to year, is if your links don't work anymore. Let me try this one more. If not, we'll go. Okay, so this, let's see. All right, so here we go. So here what they're doing is they're changing, they have a sample of a gas here, and then they are increasing the pressure on the gas, and then looking at the volume, the corresponding volume. And so what we'll see here is that if I hold the temperature constant, right, and I'm not changing the number of moles of the gas in there, so we're just isolating pressure versus volume. And so we'll see as we increase the pressure, then the volume is going to decrease on there. So pressure and volume of a gas are inversely related to each other. All right. And let's just, while I've got these up here, we'll just look at the different simulations here. Okay. And so here what we're doing is we're looking at the relationship between volume and temperature. And so they're holding the pressure constant, and they are, in this case, increasing and decreasing the temperature. And so what we see is as the temperature increases, then the volume goes up, increases as well. Okay. All right. And then we're going to come back and talk about these. I just want to do these animations. Did I have any more? No. Okay, so let's go back to our notes now. All right. Okay. So, all right. So the pressure volume relationship is referred to as Boyle's law. All right. And it basically just says that pressure and volume are inversely related to each other. So as my pressure goes up, my volume decreases. As my pressure goes down, the volume is going to increase. All right. And then the relationship between volume and temperature is called Charles' law. And again, we kind of saw, they just had this another drawing here, but if you kind of to think about it from the particle standpoint, if the pressure is to stay constant, okay, and I increase the temperature, well, when I increase the temperature, right, I'm increasing the kinetic energy of the particles, which is going to make them hit the walls of the container more often, okay, but that would be changing the pressure. So in order for the pressure to stay constant, the volume has to increase. In other words, giving them more space so that the frequency of the collision stays the same as the kinetic energy or the temperature of the particles is increasing. Okay, so we have that. Let me go back up. And we'll do our, all right. So we had here, we have that volume is directly proportional to temperature. All right. And then here we have that pressure is inversely proportional. So it's directly proportional to 1 over the volume, essentially. And we'll keep going down here. All right. And Gay-Lussac's law looks at pressure versus temperature, okay, and says that these are, again, directly proportional. So if the temperature goes up and I'm holding the volume constant, right, the particles are moving faster, so the frequency of collisions is going to increase, which means my pressure is going to go up. So pressure is directly proportional to the temperature. And then Avogadro's law is relating volume and the number of particles. And so here, again, as we can see, if the pressure and, it's the wrong diagram there. If the temperature and pressure are constant, if I increase the number of moles of particles, right, the only way I can do that and still have the pressure stay the same is I got to have more volume. I got to spread them out more so that the collisions, frequency of collisions stays the same. So volume is directly proportional to my moles. Okay, so now what you'll see is that, and we're going to talk about this ideal gas law in a little more detail later, but what you'll see is if I bring them all together, all right, if I have one statement of this relationship, things that are directly proportional to each other are going to be on opposite sides of the equal sign. If they are inversely proportional, they're going to be on the same side. So if we look here, this thing we call the ideal gas law, that is bringing together all of those relationships that we just talked about. Okay, excuse me a minute. Let me get them a dog biscuit so that they will be quiet. All right. Okay. Sorry about that. Okay. So for today, what I want to do, and let me see if I, in my notes, do I? Yeah. So let's look at where that's going to come from. So here we have pressure, volume, N is number of moles, T is temperature, and R is our gas constant. Okay, and that comes into play in that, so if we go back up to one of my proportional statements here, okay, so like here, where you have this proportional symbol, if I want to translate that into an equals, I have to have some kind of a constant because V is not equal to N, V is proportional to N. So that means that V is equal to some kind of, I'll use K for a constant, some constant times N, okay, that they're proportional. And so that's where that R value comes in, is when I combine all of those proportional relationships, I have to have some constant that's in there. And so if I rearrange this equation here to set it equal to that constant, then I get R is PV over NT. Okay, and so what that means is that if I have a gas that's at a certain set of conditions, okay, and then I change those conditions, all right, so a new set of conditions, then PV over NT, that proportional, that's always going to be equal to that gas constant. Okay, and so what that lets me do is I have this nice little equation then where I have P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And so this is combining all of those gas laws. So the way this works, and I don't ever like to have to memorize tons of equations. So with this one, essentially, rather than having to think about, okay, the pressure and the volume is changing, so that's Boyle's law, and so I need to use that. What you do to use this equation is that whatever is being held constant, you just drop that out of the equation, and what's left will be the equation that you need to use. And so we use this here whenever we have something is changing. Okay, tomorrow we'll look at when do we use that gas law with the gas constant. But for today, we're gonna use this whenever things are changing. Now, with our gas law, anytime we're using the value R has these units here. So if I'm using an equation that has R in it, then my volume has to be in liters, pressure has to be in atmosphere, temperature always has to be in Kelvin, no matter if you're using R or not. Temperature always has to be in Kelvin. And then, of course, N is moles. For this equation here, where things are changing, as long as my volume is in the same units or my pressure is in the same units, I don't necessarily need to convert those. Again, temperature, no matter what, that is always in Kelvin. Okay, so now let's take a look at, let's see, did I put some examples in here? Okay, no, those are not the ones I want. Okay, let's go. I put a worksheet with some practice problems in Otis. So let's just take a look at some of those. Okay, so this one here, I have a volume and then a temperature and a pressure, and it's asking me for what will the new volume be if I change. So I'm changing my conditions there. Okay, so here's my V1 and my T1 and P1, and then this is my T2, P2, and then it's asking me for what's the new volume going to be. All right, so I always do my same P1 V1 over N1 T1 is P2 V2 over N2 T2. All right, and so the thing that's not changing is my moles, so I just drop that out. All right, and I'm left with the equation that I'm going to use. So here I have, and my second pressure is in torr, so I'm just going to leave that there. So I have that standard pressure is 760 torr, and then I have 68 milliliters over, and this is in Kelvin, so standard temperature is 273 Kelvin, and then my T2, it's 30 Celsius, so plus 273 to get it into Kelvin. So that's going to be 303 Kelvin there. So I have 273, and that's going to equal, my second pressure is 725. V2 is what I'm solving for, and it's at 303 Kelvin. So let's see, that gives us 760 times 68 times 303 dividing by 725 times 273. So I'm getting 79.1, and that's in milliliters. Okay, let's look at, let me see if I can pull a subset of these over. Just going to put them on another page so I have more room. There we go. That's better. Okay. All right. So here we have, that's our V1. And then here, T1 is going to be 27 plus 273. So that's 300. And it's asking for V2, and my T2 is 273. All right. So again, P1, V1, for N1, T1 equals P2, V2 over N2, T2. So let's see, moles are not changing, pressure is not changing. So there's my equation. So I have 515 milliliters over 300 is equal to V2 over 273. So my volume, 515 times 273 divided by 300. So I get 468.65 milliliters. All right. And so number 9, V1, and I have a P1. It's asking for V2, and it's giving me a P2. So here, start out with okay, and so here the moles stay the same. I'm not changing the temperature. Okay, so there's my equation. So I have 785 times V1 is 525. It's going to equal to 745 times V2. So V2 is, let's see, 785 times 525 divided by 745. So I'm getting 553.2 milliliters on there. Okay, let me see if there's any others we need to look at. Let's do, all right, let's do those two there. Okay. So now, all right, so here we have, there's our P1, and our T1 is 27 plus 273, so that's going to be 300. And we have a T2, and it's asking for P2. All right, so 33 P1. All right, so moles are staying the same. It's a cylinder, so the volume is not changing either. So we have, or it's a can rather, not a cylinder, but all right, so I have one ATM over 300 is equal to my second pressure at, 927 plus 273. So that's, I get 1200. So 1200 divided by 300, so my P2 is equal to 4 atmospheres. All right, and okay, let's do this one, and then there's one more I wanted to do. I think it's in the notes. Okay, compressed oxygen gas. Here's our V1, P1, T1 is 27 plus 273, so that's 300. And says my pressure P2. All right. And here, because this is a rigid cylinder, V1 and V2 are going to be the same on that. So 34 P1 over N1 T1 is equal to P2 V2 over N2 T2. So my volume is staying the same and the moles are staying the same. So I get 100 ATM over 300 Kelvin is equal to 5 ATM over T2. So 5 times 300 divided by 100. So I get that T2 is 15 Kelvin on there. Okay, so let's go back to the notes. There is a problem. And so in the videos that I posted, the other videos, it has me working through these, but this one is this is sort of, I don't know if you can have classic chemistry problems. This is like a classic problem that you'll see for sure in your college chemistry class. Okay, so here we have on this side, it says it's 5 liters and has nitrogen gas at a pressure of 0.75 ATM. And then so these are separated by a valve here. And the second flask, this is 8 liters and has oxygen at a pressure of 1.25 atmospheres. And so basically it says when you open that valve and allow the gases to mix, what is going to be the pressure of the resulting mixture. And so the key thing here is that one, with gases, as far as using the gas laws, it doesn't matter that it's nitrogen and oxygen mixing. A gas particle is a gas particle. on that. And so what we want to think about is that the total pressure that I have is going to be equal to, in this case, so this is my oxygen, this is my nitrogen. And so my total pressure here in the flask is going to be equal to the pressure of the nitrogen plus the pressure of the oxygen in when they spread out in that whole volume. And so essentially what we want to think of this as, if that's my V1 and P1, and this is my, for the oxygen, that's my V1 and that's my P1. And so essentially what we're doing is, in both cases, we're changing the volume and then looking at what the resulting pressure is. So V2 is going to be, we're going to add the two volumes together. And so 5 plus 8. So we get V2 is going to be 13 liters. So I'm going to do here, if we do our P1, V1, 1, T1, is P2, V2, into T2. So for both of them, moles is staying the same, temperature is not changing. So I'm going to do, for my nitrogen, right, I would have 0.75 times 5 is equal to P2 times my new volume, which is 13. And then the same thing over for the oxygen. I'll have 1.25 times 8, so P1V1 is equal to P2 times the new volume, which is 13. So solving that, so I have 0.75 times 5 divided by 13. So I'm getting a P2 here is 0.288. And then over here, 25 times 8 divided by 13. So my P2 here is 0.769. So my P total in the flask, once I open the valve, is going to be 0.288 plus 0.769, which would be I get 1.06 atmospheres. Okay. Any questions about any of those? So today we're focusing on using gas laws when we have something is changing on there. And so there's a quest assignment. It has these types of problems, and I think there's a couple where maybe you have to convert between different pressure units on there. So any questions? Okay, I will, well, let me see, wait, did I create a new, let me go, hang on, let's go here. I think I made a new Jamboard already. Let me see. Yes, so you should have gotten shared with you a Jamboard for Unit 5. So that'll be where I'll look for any questions on the quest problems if you want to post them there. All right, if there aren't any questions, I think we're done for this morning. You guys have a good day, and again, if you have any questions, just post them on the Jamboard. All right, I'll see you guys tomorrow. Let's see.